Alright, this is our final sample problem with the video for titration. It's also, unfortunately, the most difficult one. While it still involves redox reactions, this will be your first problem with a back titration. So for this video, I'll try to be more slow or more accessible so that you won't get lost with this new concept. Let's read the problem together. The carbon monoxide in a 20.3 liter sample of gas was converted to carbon dioxide by passing the sample over iodine pentoxide heated to 150 degrees Celsius. So that's iodine pentoxide plus 5 moles of carbon monoxide forming 5 moles of carbon dioxide and 1 mole of iodine. The iodine, alright, so this iodine, the iodine was distilled at this temperature and was collected in an absorber containing 8.25 milliliters of 0.01101 molar sodium thiosulfate. Alright, so this iodine, because it's a gas, to collect it, it was made to react with thiosulfate, forming iodide and S4O6. The excess sodium thiosulfate was back titrated with 2.16 milliliters of 0.00947 molar iodine solution. Alright, so again, remember that we used this amount of sodium thiosulfate, but this is in excess. We actually, after this reaction, we actually have some thiosulfate remaining. And it was that thiosulfate that was titrated with 2.16 0.00947 molar of iodine solution. Our goal here is to calculate the concentration of carbon monoxide in milligrams per liter of sample. It's quite a loaded problem, isn't it, guys? So before I will move on, I think I should try to spend some time to explain what a back titration really is. In problems 1 and 2, we did a direct titration. Again, if you remember, whatever was titrated or whatever was in the volumetric flask, in the Erlenmeyer flask, that already contained the analyte. So the titration results could be immediately used to calculate for the concentration of the analyte. But in this case, we're doing a back titration. Although our analyte is iodine, or is carbon monoxide, we had to convert it into iodine, and the iodine, since it was a gas, had to be captured by thiosulfate. So from here alone, you could imagine the steps of conversions, stoichiometric conversions, we have to go through to get back into carbon monoxide. Alright? So our analyte in a back titration, in this case, our analyte is carbon, right? But we are actually measuring iodine. Our analyte is made to react with a reagent. The excess of the reagent is then measured. Alright, so why is it done this way? First and foremost, if we were not able to capture the iodine, then we had nothing to measure. We can't measure carbon monoxide directly, that's why we had to convert it into an iodine form, which was throughout the course of the reaction limited by the amount of carbon monoxide. So at the end of this problem really is a complicated sequence of chemical reactions that we can actually conveniently arrange so that starting from thiosulfate, we can end up with carbon monoxide. So unlike the direct titration where the analyte is being titrated directly, for a back titration, another reagent is being titrated. But because we know some information about that reagent, we can use some clever manipulations to relate the values of that reagent back into a form that can be useful in describing the analyte. Alright, so I don't think it's very clear for you right now, so the best way to proceed is to try solving the question. Let's write down the given first. Let's write down the given again in sequence. So we have a 20.3 liter sample with with carbon monoxide. The carbon monoxide was converted into carbon dioxide, forming iodine as well. Iodine was collected in 8.25 milliliters, 0.01101 molar sodium thiosulfate, and A2S2O3. Excess S2O3 was titrated with 2.16 ml of 0.00947 molars of iodine. We're asked to provide the milligrams per liter of carbon monoxide. 28.01 grams per mole. So, as always, I told you to start from the end, right? Although I do encourage you to construct solutions in one line only, in one straight calculation, so that you will not have to round off and introduce errors in your calculations. At this point, since it might be difficult for you to understand, I will present the solution in discrete steps. Alright? So I will be rounding off, but I will try to round off I will try to avoid rounding off as much as possible. But hopefully by presenting and dividing the solution into steps, it will make more sense for you. So from the flowchart, let's start from the back or the bottom. What will I get if I multiply 2.16 ml and 0.00947 millimoles per ml of I2? This is the titration part, right? If I multiply the volume and the concentration, I should be able to get the millimoles of iodine. But that's not really helpful for me right now, because it was not this iodine that is related to the reagent, but it was what the iodine was reacting with. Alright? So if I multiply these two values, I get millimoles of iodine. But I'm more interested in the millimoles of thiosulfate. From this chemical equation, I know that for every millimole of iodine, there should be 2 equivalent millimoles of thiosulfate. This means that whatever was titrated at the final part of the problem describes the thiosulfate that was not able to react with the iodine arising from our analyte reaction. Alright, again, this equation is the millimoles of thiosulfate in excess. Alright, so let me calculate this value first. 2.16 times 0.00947 times 2. Although it's 3 significant digits, I will not round off for the meantime. 0.409104 millimoles. So we're done with this step of the flowchart. Note that we started with this amount, 8.25 ml, 0.0110 molar. So if I take 8.25 milliliters and multiply with 0.01101 millimoles per ml, that should give me the millimoles of thiosulfate that was added initially. Alright, so again, we started with 8.25 times 0.01101 molar. So that amount of millimoles of thiosulfate was made to react with the iodine evolving from our analyte reaction. And the unused iodine was was measured in a titration with this step of the problem. So initially we had 8.25 times 0.01101, that's 0.0908325. So, how do we rationalize this? Let me show you a sample chemical reaction. If I am making squares react with circles to form a square circle chemical, if only one square is needed to react with one circle, we have two squares remaining, right? So, it makes sense that after this reaction, we measure this by titration, for example. And if we take the 3 squares initially, subtract it with the 2 squares after the reaction, we get the 1 square that was used up in the reaction. But we also know that 1 square can be converted to 1 circle. Alright? So, through these logics, I can convert my thiosulfate back into iodine, which I can convert back into carbon monoxide. Again, if I take my initial amount of reagent, subtract the excess amount, I get the amount that was made to react with my chemical. So, if I have 0.0908325 millimole minus 0.0409104 millimole, this is the millimole of thiosulfate that reacted with iodine. Alright? So, 0.0908325 minus 0.0409104, this amount of thiosulfate reacted with iodine. Alright? So we're done with this step. All we have to do now is to convert thiosulfate into iodine and convert the iodine into carbon monoxide and then convert that to milligrams and divide it by the overall volume. Again, we already have the moles or the millimoles of thiosulfate that reacted with iodine. So we can use stoichiometry to calculate for the millimoles of iodine. And from the millimoles of iodine, we can convert back into the millimoles of carbon monoxide, which is our analyte. Okay? Okay, I ran into some technical difficulties and I need to reshoot this part. But anyway, we have 0.0499221 millimoles of thiosulfate, right? As I told you earlier, we can convert this into iodine based on this chemical reaction. We know that for every 1 millimole of iodine, that is 2 millimoles of thiosulfate. 1 millimole iodine, 2 millimole thiosulfate. Now that we have iodine, we know that 1 millimole of iodine is 5 millimoles of carbon monoxide. Again, that's 1 millimole iodine, 5 millimole carbon monoxide. And we know that 1 millimole carbon monoxide is 28.01 milligrams. Alright, if I look at this expression, I am left with milligrams of carbon monoxide. Since I need to show milligrams carbon monoxide per liter of sample, I just need to divide by the liter of the sample, which is 20.3 liters. Back to my trusty calculator, that's 0.0499221 divided by 2 times 5, was it 5? Times 5 times 28.01 divided by 20.3. The answer is finally 0.172 milligrams carbon monoxide per liter. Again, 3 significant digits based on the given values. Were you able to follow with my calculations? I understand that it's quite difficult and different for you, so I really am not expecting that you perfect it during your first watch. I highly suggest you go over this problem again, go over this video again, and try solving this problem without my help. Again, it is a very difficult concept for a lot of students, but at the end of the day, we still will need to do stuff like this in the future. So it would be very helpful for you if you really revisit everything and make sure that you understood the concepts and the steps of the calculations. Again, it's just simple conversions, just simple stoichiometry, but what you really need to practice is to imagine the process and the logic of the problem. And ultimately, that skill will transfer with various other chemical problems in the future. So I hope you learned something from these 3 sample videos, and I'm excited to hear what you think during the synchronous session. I'll see you then.